In this video, I will list the 5 most important properties of definite integrals. Here they are all at once. In a moment, I'll go through them one by one. Once I explain them, these properties are all pretty intuitive. They make sense geometrically and they are easy to believe. Of course, to be rigorous, we would need to prove them, and we should do it from the definition of integral. I will skip the proofs in this video. Let's begin. The first two properties say that definite integrals are linear. What does this mean? The integral of the sum of two functions, f and g, equals the integral of f plus the integral of g. And the integral of a constant c times a function f equals the constant c times the integral of f. Linearity means these two properties. You probably already assumed they would be true, and we're going to use them anyway. I should clarify that what I wrote by itself is a bit sloppy. To be more rigorous, I should write these properties as theorems, and I need to specify which functions must be integrable where. For example, the rigorous way to write the first property is this theorem. Let f and g be bounded functions on the interval ab. If both f and g are integrable on ab, then f plus g is also integrable on ab, and I get the equation from above. But if f and g are not integrable, then the sum may or may not be integrable and the equation does not apply. This is the same as the limit laws or the differentiation rules. I will leave it as an exercise for you to write the second property as a theorem. In any case, the equations alone are a good way to summarize the properties and to remember them. Let's move on to the third property. It is about comparing integrals of the same function over different intervals. This one is best explained with a picture. Here I have the graph of a function f and 3 points a, b, and c in this order in the horizontal axis. In this picture, the integral from a to c represents this area. The integral from a to b represents this area, and the integral from b to c represents this area. This suggests that the integral from a to c equals the integral from a to b plus the integral from b to c. This makes sense geometrically, and indeed, that is the third property. Like before, if I want to be rigorous, I can write this as a theorem, and I have to pay attention to what must be integrable where. The theorem says, I begin with a bounded function f on the interval ac, where a is less than b less than c. If f is integrable on the two smaller subintervals ab and bc, then we can conclude that f is also integrable on the bigger interval ac. And we get the equation above. And that's the third property. But we can expand this a little bit. So far, we had only defined a definite integral from a to b when a was less than b. Let's go further. Here's a new definition. I am going to declare that the integral from b to a is minus the integral from a to b. I can do this. Up to this point, we had never integrated backwards. This is a new concept. So I get a new definition for it. From now on, this is what a backwards integral will mean. And in addition, the integral from a to a will always be 0, by definition. This is extremely useful. With these new definitions, the identity I had, that the integral from a to c is the integral from a to b plus the integral from b to c, is true no matter the order of the numbers a, b, and c. For example, if c is between a and b or anything else, even if some of them are equal. I will leave the proof as an exercise. It is a proof by cases, depending on the order of a, b, and c. Many cases. But let's look at one case as an example, to show that this notation is reasonable. Let's consider the case when a equals c. Then I have the integral from a to b plus the integral from b to a equals the integral from a to a, which should be 0. In other words, this equation says that the integral from b to a equals minus the integral from a to b. Great. This example is not a proof. This example suggests that the new definitions are reasonable, they make sense, they are consistent. So once again, this identity is true for all values of a, b, and c, as long as the function is integrable where it needs to be. The fourth property deals with the geometric interpretation of integral as area. That was our original motivation to define integral, but this time I want to go a bit further. As you know, if I have a function f like this one over an interval ab, the integral of f from a to b is the area of the region between the graph of f and the x-axis, shaded in light blue in this picture. However, In this interpretation, we had always been assuming, perhaps implicitly, that the function f was positive. What if f isn't positive? Think back to the definition of integral. Upper and lower sums, upper and lower integrals. At no point in the definition did we need f to be positive. The definition is exactly the same for positive or negative functions. In other words, we have already defined integrability for bounded functions, regardless of whether they are positive or negative. However, we only had a geometric interpretation of the integral as area for positive functions. So far. So, what does the integral represent for a negative function? For example, this one? In this case, the integral is minus the area between the graph and the x-axis, in orange in the picture. Why? Think back to the definition of integral. The heights of the rectangles in the upper and lower sums are values of f, and are therefore negative, but other than for the sign, the upper and lower sums are still measuring area. If necessary, pause the video to convince yourself of this. And what if I have a function that takes both positive and negative values? Putting together what I just said, plus the previous property, we can split the region between the graph of f and the x-axis into two pieces. The integral will be the area of the piece of the region above the x-axis minus the area of the piece of the region below the x-axis. There are many other types of region whose areas we can write as integrals, but I will leave it at this for now. Just to make it very clear, areas are always positive, but definite integrals may equal plus the area or minus the area. Finally, the last property deals with inequalities and integrals. If I have two functions f and g, and f of x is less than or equal to g of x for all x in the interval, then the integral of f is less than or equal to the integral of g. This one also makes sense geometrically. Just compare one area with the other area. Unlike the other properties, I should write it more rigorously as a theorem, paying attention to what must be integrable on what, but I will leave that as an exercise. And that's it. These are the 5 most important properties of definite integrals. I have a final comment. Pretty much everything you will ever need to do with definite integrals relies on these 5 properties and nothing else. To a certain extent, if you don't care about rigorous definitions or proofs, you could forget the formal definition of integral, take these 5 properties as your starting point, and you could be well equipped to solve problems.